Welcome to lesson 14 of the Advanced Higher Course Spec. In this lesson, we will be looking at normal approximation for binomial sample proportion. You'll find this skill on page 25 of the Advanced Higher Course Spec. At the end of this lesson, you should be able to use appropriate notation when working with sample proportions. You should be able to normally approximate to the binomial, and you should be able to calculate the standard error for sample proportions. We'll start off with notation, and then we'll move on to standard error. The notation, there's only two things to note here, is that we have p hat and q hat, and what these mean is that the probability for success in sample, or like derived from the sample that we had, q hat is probability for failure, which we've also gotten from the sample. Now, similarly to x bar versus mu, x bar is a sample mean, not a true mean. So we give them different notations to show that this is not the true value. It could be, but most likely it's not because it's from a sample, it's not from a census. So, and how we show the same for probabilities is just with normal p, we have the true probability for success, and for normal q, we have the true probability for failure. And as always, you can get p hat by doing 1 minus q hat. You can get q hat by doing 1 minus p hat, and then you can get p by doing 1 minus q. You can get q from doing 1 minus p. That was covered in a different lesson. Next, let's move on to standard error. So we know for normal calculations, not involving proportions, the formula is sigma over root n. So if we want to derive it, let's first try and get sigma, or our standard deviation, because we don't know our true sigma because we have a sample. So one thing I would do here first is we know that variance is equal to the standard deviation squared. So first I would do here is get standard deviation from our proportion. Now in our binomial, it says here our variance is npq. So that is for normal numbers. When we convert to proportions, we divide everything by n. So our mean becomes the proportion of people who, or a proportion of events that succeed. And our variance, which used to be npq, just turns into n, not n, turns into p and q. So what that means, if we square root that, we get s. So s would be square root of pq. Now we can input this, we can replace sigma with s, and that would give us some error is equal to root pq over root n, and then we can just simplify that and put everything in a square root. Root pq over n is our standard error when we're dealing with sample proportions, which follow a binomial distribution. Now let's try the following question. A random sample of 40 is taken from a football team's game and found that the team wins 5 out of 8 of its games. Of the next 24 games, what's the probability that the team will win at most 18 games? First thing I do here is I write the probability of success with 5 over 8, which is 0.625. Probability of failure, which is 0.375. Number of trials, which is 24. And now I would normally approximate this distribution. You can write a binomial if you want, but I would just go straight to probability is roughly equal to n 0.625 and variance, which is 0.234. Next thing I do here is I find z. So z is equal to 18 over 24, which is 0.75 minus the supposed mean, which is 0.625 over standard error, which is root of variance, which is 0.234 over root of the number of the size of the sample, which is 40. And that gives us a z value of 1.63. Next thing we have to do is we have to find a probability of getting that z value or less. The probability of z being less than or equal to 1.63, which is 0.9484. And there's no continuity correction because a proportion is continuous, whereas a normal binomial is discrete. Question? And as always, I recommend you all do the question before I go through it, but it's your choice at the end of the day. A random sample of 40 is taken from the football team's games and found that a team wins 5 out of 8 of its games. For the next 24 games, what's the probability that the team will lose at least 18 games? So it loses at least 18, or it can lose 19, 20, 21, 22, so on. Now, how would I write this? I would write this probability of failure or fail is greater or equal to 18. That's what we're trying to figure out. Or you could turn this the other way around and say the probability or the number of wins you have is less than or equal to 17. And when you do that, it becomes exactly the same as last question, very easy. We already know p hat, q hat, all that stuff. We even know our normally approximated distribution is 0.625 and 0.234. Then again, we find z, so 17 out of 24, so the probability for that is 0.7083 minus 0.65 over standard error, which is standard deviation, which is the square root of variance, which is 0.234 over the sample size, which is 40, and that gives us 1.09. And then if we use our normal distribution table, 1.09, we get 0.8621. The probability of z being less or equal to 1.09 is equal to 0.8621. Let's do this final question. The question is a lot smaller because we need a lot of space. It's a slightly tricky question. Of the next 24 games, what's the probability that the team will win at least 16 games, but at most 20 games? So what I like to imagine here is, not even imagine, what I like to do here is I like to draw this normal distribution to get an idea of what this question is asking me for. So the team wins 5 out of 8 games and it's going to do 24 games, so it will win 15 games on average. What this question is asking me is the probability of it being between 16 and 20 that win the number of games won. It's asking for this range here. And normally what we're used to is for us to be asked a question of, what was the probability of the 18 being the max number of games you win. So there wouldn't be any kind of lower barrier, it'd be an upper limit, like 18, or in this case 20. But let's have a shot at this question. So the distribution is the same. P hat is roughly equal to 0.625 and 0.234. And what I'm going to do here is I'm going to find the probability of x being less than or equal to 20. I'm going to find a probability of x being less than or equal to 16. If I take away both of them, I should get the probability of 16 being less than x, which is less than or equal to 20. And that is what the game is asking us. So let's do that. The probability, so first let's find a z value. Let's find the z value for the probability of x being less than or equal to 16. And how we would do that is we would do 0.6667 because we're doing 16 over 24 minus 5 over 8. So that over 0.625 over our standard error. And that gives us 0.42. So the probability of z being less than or equal to 0.42 is 0.6628. So we can put that in this equation, 6628. Now let's find our second z value. So we do 20 over 24, which is 0.8333 minus 0.625, again over the standard error. Make sure the square root goes all the way down the fraction, or you would lose a mark. And that gives us 2.1, and a probability of z being less than or equal to 2.1 is 0.9821. We can put that here as well. So 0.9821 minus 0.6628. 0.3193 is the answer. One way to visualize this is, let me erase all this. It's kind of like with a few pictures. So if these are the means, these last lines, and we were asked to get this kind of shaded region, what I did was I found the region covering from 20 and less. I found the region coming from 16 and less. I took them both away, which brought me to the region here. And if these pictures don't make sense to you, don't worry. If you understand the maths, that's good enough. That is the end of the lesson. By now, you should be able to use appropriate notation when working with sample proportions. You should be able to normally approximate a binomial, and you should be able to calculate the standard error for sample proportions.